Chapter 5 focuses on thermochemistry, which is a subset of thermodynamics. We will have another chapter later in the semester that focuses specifically on chemical thermodynamics. But this chapter, thermochemistry, is a subset of thermodynamics. Thermodynamics is the study of energy and its transformations. Thermochemistry focuses on heat flow in chemical reactions. So, as an engineering major, you're going to have to take another course in thermodynamics, and so you'll find all this be very helpful to you. We start off with one of the thermodynamics terms that we need to be familiar with whenever we do thermochemistry or thermodynamics, and that's the term state function. Now, you need to know what a state function is. A state function is, first of all, it's a property of a system. It's a property of a system that is independent of the history of the system. A property of the system that is independent of the history of the system. It's independent of the path followed to get to that point. Okay, so it might be helpful here to list some examples of state functions. Some examples of state functions. Examples of state functions would include, for example, the temperature of the system. The temperature that the system has right now is completely independent of what its temperature was 5 minutes ago or 1 hour ago. It's independent of the history. The volume, if you're dealing with a gas, the volume of the gas is independent of its history. It doesn't matter what the volume of the gas was yesterday or 5 minutes ago. Volume describes its current state. We have temperature and volume. The pressure of a gas is a state function. The molarity of a solution, remember capital block M stands for molarity. Those are state functions. And then some thermodynamic terms that are important. Capital E stands for the total internal energy of the system. It's a state function. And even the change in energy. If a system undergoes a change from one amount of energy to another amount of energy, the delta E, the change in energy, is independent of how it got from point A to point B. And then this chapter focuses on enthalpy. H stands for enthalpy, which you can think of as like heat, but it's not heat, and it's not heat in the sense that the delta H, the change in enthalpy, is a state function. It does not depend on the pathway that's followed. Now, here are some things that are not state functions. Here are some things that are not state functions. Two things that we can describe a lot in this chapter that are not state function are heat, which we abbreviate with the lowercase q. Now, delta H, we often think of delta H as heat. Delta H is the enthalpy change, and we can think of it as heat flow, but it's not heat because heat is not a state function, but enthalpy change is a state function. The heat flow depends on the path that's followed. The amount of heat that's given off or absorbed depends on the path that's followed. The enthalpy change does not depend on the path that's followed. It does not depend on the history of the system. And then a second thing that is not a state function is work. So we will talk about work. The amount of work done depends upon the path that's followed. So when this says which of these is not a state function, the correct answer is heat. Enthalpy is a state function. Temperature is a state function. Volume is a state function. And the internal energy, capital E, of the system is a state function. So the correct answer is A. Number 2 asks about which of the following processes is endothermic. Now, if something is endothermic, then that means that if it's endothermic, delta H is a positive value. If you have an exothermic reaction or an exothermic process, then delta H is negative. If it's endothermic, then it absorbs heat. If it's exothermic, it releases heat. Well, one of the things we can write off, we can immediately focus on will be the two chemical reactions that are listed here. Choice A and choice C are chemical reactions. Choices B and D are simply physical changes. A and C are combustion reactions. And you need to know that combustion reactions are always exothermic. That's one of the things that describes and defines a combustion reaction. They're very exothermic. They release a lot of heat. So choice A is the combustion of hydrogen gas. It reacts explosively with oxygen gas to form water. That's a combustion reaction. It's exothermic. And then choice C is a combustion reaction. Methane reacts with oxygen to form carbon dioxide plus water. That's an exothermic process. That's very exothermic. Okay. Well, the other two processes are physical changes. B and D are physical changes. They're phase changes. B is when a gas goes to the liquid phase. We call this condensation. D is when the solid phase goes to the liquid phase. This is called melting. Those are physical changes. So you need to know whether or not a physical change is endothermic or exothermic. And here's how we can approach this. I'm going to draw an enthalpy diagram right over here. And on this enthalpy diagram, if you have a pure solid is relatively low in enthalpy. So it's at this level on this enthalpy diagram. But higher in enthalpy is a liquid. And in fact, to go from the solid to the liquid, which is melting, that is an endothermic process. It has to absorb heat. The delta H, which would be the enthalpy content of this level minus the enthalpy content of this level, is positive. And so this is an endothermic process. And then to go from the liquid phase to the gas phase. A gas phase is much higher in enthalpy than a liquid, and it absorbs a lot of heat. And that's an endothermic process. Okay. To go from the solid phase directly to the gas phase is called sublimation, and that's also endothermic. So in these processes, we see that delta H is positive, so that these processes are endothermic. Well, that rules out choice B when, that rules out choice D, rather. When ice melts, that's an endothermic process. So that rules out, or actually that's the correct answer. This asks which is endothermic. Well, the solid going to the liquid phase is endothermic. It absorbs heat, and that's the correct answer. Now let's look at the other phase changes. I'm going to extend these lines over here. So this is the solid, the liquid, the gas. So in this case, if you go from the gas to the liquid, that's called condensation, and that's exothermic, and that's what we have here. The gas to the liquid is exothermic, and so that is not an endothermic process. If you go from the liquid to the solid, that's freezing, and freezing is an exothermic process. Or if you go from the gas directly to the solid, that's called deposition. In these three cases, the delta H has a negative value, and each of these are exothermic. Now, be sure that you understand that this diagram that I have drawn, this describes physical changes only. Physical changes. This is not a chemical reaction. These are physical changes. They are the phase changes of a pure substance. The phase changes of a pure substance. Okay, so the correct answer to number 2 is choice D. So we can rule out E as being none of these. So going from the solid to the liquid is an endothermic process. Okay. Number 3, ask you to compare the enthalpy change to the change in the internal energy of the system. And this is also work, and this is also Q. Now, in order to understand this, you need to know the first law of thermodynamics. And the first law of thermodynamics can be expressed algebraically. The first law of thermodynamics says that energy is conserved, and we can express it algebraically by saying delta E equals Q plus W. So delta E is the change in the internal energy of the system. Q is heat, and W is work. Now, what you need to keep in mind is that the work done by expanding gases, the work done by expanding gases is negative P delta V. This is when the pressure is held constant. If you have a gas under constant pressure conditions, then work is equal to negative P times the change in volume. So if you look at the second choice, the heat gained or lost by a system under constant volume, the heat gained or lost by a system under constant volume conditions. If under constant volume conditions, so I'm just going to say here, under constant volume, if work is equal to negative P delta V, then delta V is 0. If the volume is constant, the change in volume is 0, and work is equal to 0, and therefore delta E is equal to Q plus 0. Look, instead of Q plus work, well, work is 0. Delta E is equal to Q. What does Q stand for? It stands for heat flow. So the heat gained or lost by a system under constant volume, if you look at this equation, let's rewrite it. Delta E equals Q minus P delta V. That's another way to state the first law of thermodynamics under constant pressure conditions. But if the volume is constant, then delta E is equal to the heat flow under constant volume conditions. And so the second choice is delta E. The second part of this question is delta E. Now the first part of the definition, this is the definition of enthalpy. So the enthalpy change is defined to be the heat gained or lost under constant pressure conditions. So that delta H is the heat flow under constant pressure conditions. We denote that with the subscript capital P, Q sub capital P. This is the delta H. That's the definition of enthalpy change. And so the correct answer to number 3 is choice A. Number 4. A gas expands at a constant temperature from a volume of 14 liters to a final volume of 27 liters against a constant external pressure of 50 atmospheres. Calculate the work that's done in this case. Well, in this case, first of all, we didn't know, is the work considered positive or negative? Now, remember that the point of view is always the point of view of the system. So we have a gas that's expanding. So if this is a steel cylinder and we've got a gas inside here, here's a movable piston. And if the gas expands so that now it's pushed up this piston, then the question is the work positive or negative? Is the work positive or negative? Well, you need to focus on the fact that in this class, we will always determine the work from the point of view of the system. And so the point of view of the system is inside, it's the gas itself. I'm going to draw a little stick figure. That represents where our point of view is. Our point of view is from inside this. And if we're pushing up, we're pushing up. In this case, work is negative. In this case, work is negative. And so I can rule out choice A and choice C. Work will have a negative value. Whenever the system does work, work is negative. Let's just write this down. If the system does work on the surroundings, then work is negative. Okay. Now, the rest of this will be a calculation using the definition that I mentioned up here. And that definition is that the work of an expanding gas is equal to negative P delta V. Now, I'll put negative, and the pressure that's done here is 50 atmospheres, constant pressure, negative 50 atmospheres. And delta V. Now, in chemistry, you need to always know that delta V is final minus initial. The final volume is 27.0 minus the initial volume, which is 14.0 liters. Okay. So we'll just put here that work is equal to, whenever I multiply these two together, now I have this in liter atmospheres, which is not the appropriate unit, so I need to convert this. Let's write it this way: negative 50 atmospheres. That's the P. The delta V is 13. 27 minus 14 is 13 liters. Now I need a conversion factor. Notice you do not have to memorize this for the exam. I'll give you this conversion factor, which is that there's 101 joules per every 1 liter atmospheres. And if you focus on the units, then you will see that atmospheres cancels and liters cancels, and I end up in unit of joules. And this will calculate out to be, I've run out of space here, but this calculates out to be negative 65,650 joules, and it's most common to represent this in kilojoules. It's an easier to use unit, and so we will round this to negative 65.6 kilojoules. Negative 65.6 kilojoules. So E is the correct answer. Be sure to convert liter atmospheres to joules using this conversion factor. Okay. Number 5 says the overall reaction that occurs in some commercial heat packs is represented this way. What is the enthalpy change when 11.2 grams of iron reacts with excess oxygen? Now, first of all, I want to point out that this is a thermochemical equation. This is a thermochemical equation. A thermochemical equation is a balanced equation that has the delta H, the enthalpy change, written out to the side of it. And the most important point about a thermochemical equation is that these coefficients, 4, 3, and 2, refer to the number of moles of reaction. Okay, so the coefficients in a thermochemical equation refer to moles of reactants and products. Refer to moles of reactants and products. Okay, so we can solve this problem like a dimensional analysis problem if we keep in mind that it's only negative 1,652 kilojoules if 4 moles of iron reacts with 3 moles of oxygen to form 2 moles of Fe2O3. So we will set this up like a dimensional analysis problem. What do we want to know? We want to know the number of kilojoules. So I write the number sign and the unit I'm looking for, the number of kilojoules. Number 2, start with the given measured quantity, which is 11.2 grams of iron. So 11.2 grams of iron. Now this is just like a stoichiometry problem. And I will convert from grams of iron to moles of iron using the molar mass. So in the denominator, the molar mass of iron is 55.85 grams per every 1 mole of iron. Grams of iron per every 1 mole of iron. 55.85 grams of iron per moles of iron. And next, so grams of iron cancels, I have it in moles of iron. I'll bring moles of iron down here. Usually at this point we wake up screaming mole to mole ratio. This is not a mole to mole ratio, but I like to say that this is like a mole to mole ratio. This is like a mole to mole ratio. Because we get it from the thermochemical equation. In the thermochemical equation, the coefficients refer to the number of moles. Every time 4 moles of iron reacts, the enthalpy change is negative 1,652 kilojoules. So this is like a mole to mole ratio. It's not a mole to mole ratio, but for every 4 moles of iron, this is the enthalpy change. And so when we calculate that out, we would get the answer of negative 82.8 kilojoules. Negative 82.8 kilojoules. So be sure you know how to work thermochemical equations. Question number 7 says, consider 2 samples A and B of the same substance which are at the same temperature in separate containers from which no heat can escape. Sample A has a greater mass, equal amounts of heat are added. What happens in this case? Well, let's imagine this. So I have 2 containers. Now they are insulated such that no heat can escape. And so I'm going to color this in. Think of this as an insulated container. No heat can escape. So we've got some substance over here, and we have there's more A. This is sample A over here than B over here. So this is also insulated, but there's less B over here. Well, if they're at the same temperature, but we add the equivalent amounts of heat to each sample, then the temperature of B is going to increase more. The correct answer is going to be choice D. Now you can see this intuitively. If you add the same amount of heat to a swimming pool that you add to a drop of water, the drop of water is going to get a lot hotter a lot faster. Now mathematically there's a way that you can think about that, and that's with the equation that we call the MCAT equation. The MCAT equation looks like this: Q equals MC delta T. Now that's not really an MCAT, it's not an A, it's a delta T, but Q equals MC delta T. Q is the heat, M is the mass, C is the specific heat. It's the amount of heat it takes to raise 1 gram of a substance by 1 degree C, and delta T is the change in temperature. So if you were to rearrange this, I'm going to rearrange this and solve for the change in temperature. Delta T is equal to the heat flow divided by the mass times the specific heat. Now both A and B, it's the same substance, and since it's the same substance, they both have the same C, the same specific heat. They both have the same specific heat, which is the lowercase c. Now I'm going to add the same amount of heat, so Q is the same, C is the same, but one has a greater mass. The one with the greater mass, the change in temperature will be less. The one with the smaller mass will have a greater change in temperature, and that's why D is the correct answer. Okay, look at number 7. Question number 7 says, how much heat is required to raise the temperature of 10 grams of aluminum from 25 degrees C to 50 degrees C, and we're given the specific heat capacity of aluminum. Okay, so for this equation, we're going to use the MCAT equation. Q equals MC delta T. So Q is equal to, Q represents the amount of heat. M is the mass. I have 100 grams of aluminum. C is the specific heat capacity of aluminum, which is 0.902 joules per gram per degree C. Now, as always, I write this as a horizontal line instead of a slash line. It's easier to keep track of the units. And you can see that the units of grams cancels. Delta T, remember that delta T is always equal to T final minus T initial. Okay, so the final temperature is 50 degrees C, and the initial temperature is 25 degrees C. Okay, which, of course, this term, 50 minus 25 is 25 degrees C, and the units of degrees C cancels. And so when you multiply this together, then Q calculates out to be 2,260 joules. Now, in thermochemistry, we usually find it more convenient to express things in kilojoules. To go from joules to kilojoules, we'll move the decimal place 3 places to the left. This is 2.26 kilojoules. 2.26 kilojoules. And so the correct answer is choice E. Okay. Question number 8 says that a 100-gram chunk of iron is heated to 100 degrees C and then placed in 100 grams of water at 20 degrees C. What is the final temperature of this, assuming that no heat is lost to the surroundings? We're given the specific heat capacity of iron and the specific heat capacity of water. Well, in order to solve this problem, our approach needs to be there's going to be several things that we'll do. Let me just list the bullet points of what I think about here. Now, first of all, and you should be thinking this mentally. You don't have to write it down when you work the problem, but you should always think of the first law of thermodynamics in words. The first law of thermodynamics expressed in words. The first law of thermodynamics in words. Now, what do I mean by this? Well, the first law of thermodynamics says energy is conserved. So as I apply the first law of thermodynamics to this, I'm going to say the heat lost by blank must equal the heat gained by blank. Must equal the heat gained by blank. Must equal the heat gained by blank. So what's losing heat and what's gaining heat? We're putting hot iron at 100 degrees C. We're putting hot iron in cold water at 20 degrees C. So the iron is losing heat and the water is gaining heat. So the heat lost by the iron must equal the heat gained by the water. Now we can express that mathematically. And mathematically we would say Q of the iron, this would represent the heat of the iron, must equal the Q of the water. Now that's almost complete, but it's not exactly complete. If the iron is losing heat, then Q is negative. If the water is gaining heat, then Q is positive. And so I need a negative sign. So I'm going to make another bullet point over here. The question is, why the negative sign? Why the negative sign? It's because the iron is losing heat, so Q for the iron is negative, and a negative times a negative makes this positive. Water is gaining heat. The Q for the water is positive, so a negative times a negative makes this positive, and this is positive. And it does not matter, of course, which side you put the negative sign on. You can put it on either side. Now, the next bullet point, the next step in solving this problem is I'm going to use the MCAT equation. MCAT equation. Q equals MC delta T. So I'm going to rewrite this, and I'm going to say negative the mass of the iron times the specific heat of the iron times the delta T of the iron must equal the mass of the water times the specific heat of the water times the delta T of the water. Now let's just plug those numbers in. So this is the relationship that we're looking at here. And of course, the one thing you've got to watch is this negative sign. Make sure you don't lose track of that negative sign. So as I plug these in, I'll have this. I'll put negative. Well, the mass of the iron is 100 grams. 100 grams. The specific heat of the iron is 0.450 joules per gram per degree C. And the delta T of the iron, now the initial temperature of the iron is 100 degrees C. It's going to get colder, the water is going to get warmer until they're both at the same final temperature. And so the final temperature is what we're looking for. So the final temperature, T sub F, minus the initial temperature, 100.0 degrees C. Now, that's what we'll have on this side of the equation. On the other side of the equation, what is the mass of the water? We had 100 grams of water times the specific heat of the water. Now notice you don't have to memorize any specific heat capacities. You'll be given those values. 4.18 joules per gram per degree C. Times delta T. Now I will write right here just to remind you that delta T always means T final minus T initial. So for water, what is the final temperature? Well, the initial temperature is 20 degrees C. It's when you put the hot iron in, it's going to get hotter. So it's going to be T sub F minus 20 degrees C. T sub F minus 20 degrees C. And as you look at this problem, the next bullet point that I'm trying to illustrate here is that both iron and water have the same T sub F. Both Fe and water have the same final temperature. Whenever the iron and the water reach thermal equilibrium, and thermal equilibrium is when they're both at the same temperature, then they'll both have the same T sub F. So look, I have one equation and one unknown. All the units will work out correctly. The grams will cancel, the joules on both sides will cancel, and T sub F will end up being in units of degrees C in this case. So I can go ahead and multiply through and do this calculation. And when I do, then I'm going to get a negative 45.0 T sub F plus 4,500 equals, I'm not writing any units, I know T sub F will be in degrees C, equals 418 T sub F minus 8,360. I'm going to get both of my T sub F terms on the same side. So if I have a negative 45 minus 418, that's going to give me on the left side of the equation negative 463 T sub F equals, and I'm going to subtract 4,500 from both sides. So negative 8,360 minus 4,500 is negative 12,860. And now I divide both sides by negative 463, and T sub F is 27.8 degrees C. 27.8 degrees C, which is choice B. So choice B is the answer. But at this last step, whenever we're doing thermodynamics, you should always ask, does it make sense? So the question is, does this make sense? Does this make sense? And here's what I mean. First of all, final temperature must be between 100 and 20 degrees. The water's getting warmer, the hot iron is getting colder. So this is between 100 and 20 degrees. Okay, between 100 degrees and 20 degrees. Next, notice that it's much closer to the temperature of water. Does that make sense? You have the same mass, 100 grams of iron and 100 grams of water, and yet the final temperature is closer to that of water. Does that make sense? And the answer is yes, it does make sense, because water has a much higher heat capacity. The specific heat capacity of water is much higher than that of iron. Iron has a low heat capacity. That means it only takes a small amount of heat to raise the temperature of 1 gram of water by 1 degree C. It takes a lot more heat to raise the temperature of water by 1 degree C. Okay, so that's how you will work a first law question. And I would really recommend this first step. You may not want to write it down, but at least say it mentally. Okay, we'll go to question number 9 now. Question number 9 says, for which of the following could the delta H0 of the reaction be labeled as delta H0 sub F? Now the delta H0 sub F, you need to know what that is. What does the subscript F stand for? The subscript F stands for formation. Okay, and so this is what the delta H sub formation, I'm going to put asterisks here. You need to know this. This is a definition you need to know. Delta H0 sub F is equal to the enthalpy change when 1 mole, so this is a molar quantity, 1 mole, not 2 moles, not 3 moles, when 1 mole of a substance is formed, so this is the formation reaction, is formed from its elements in their most stable form. Now, if you approach one of these Roman numeral questions, don't even look at A, B, C, D, and E. Look at the Roman numerals and determine which of these is accurate. Now, delta H sub F means we're forming 1 mole. So that's the first important point. You're forming 1 mole of a substance. And because of that, you can rule out choice 2, because choice 2 in this equation, you're forming 2 moles. It can't be Roman numeral 2, because you're forming 2 moles, not 1 mole. Here I'm forming 1 mole of this compound. I'm forming 1 mole. So you're forming 1 mole. Now the next point is, are you forming it from its elements in their most stable form. So let's start with C6H12O6. What is the most stable form of carbon? The most stable form of carbon at room temperature and pressure is graphite. Yes, that's the most stable form of carbon. What's the most stable form of hydrogen? Well, you have to know that the most stable form of hydrogen at room temperature and pressure is as H2 gas. This is the most stable form, so that's accurate. What's the most stable form of oxygen? O2 gas. So Roman numeral 1, this reaction, if I put the delta H next to it, that's the same as the delta H formation. You're forming 1 mole of a substance from its elements in their most stable form. Now look at Roman numeral 3. You're forming 1 mole. So as I look at magnesium, what is the most stable form of magnesium at room temperature and pressure? Well, it's magnesium solid. And so that's the most stable form of magnesium. What is the most stable form of nitrogen at room temperature and pressure? The most stable form of nitrogen is as N2 gas. So the problem with this is that the most stable form of nitrogen is N2. You need to know the most stable form of these substances. The most stable form of nitrogen is N2 gas, not N. And so it can't be Roman numeral 3, and so the correct answer is choice A, Roman numeral 1 only. Question number 10 says that calcium carbide reacts with water to form acetylene. So this is the balanced equation, this is the delta H. So this is a thermochemical equation. What is a thermochemical equation? It's a balanced equation that has the delta H to the side. And this says, what is delta H sub F for CaC2? Okay, well, in this case, we're looking for, in this case, we are looking for this particular reaction. We're going to do Hess's law. Okay, let me write Hess's law over here. So Hess's law says that you can calculate the delta H 0 for a reaction if you know the delta H of formations. These are the standard enthalpy of formation of these substances. And it's equal to the sum times the stoichiometric coefficient of the products times the delta H 0 of formation of the products minus the sum times the stoichiometric coefficient of the reactants times the delta H 0 of formation of the reactants. Okay. So that is Hess's law, where we use delta H sub F. And I would say, just remember, it's products minus reactants. Products minus reactants. So products right here minus reactants. And that's how you can remember Hess's law. Now, I also want to point out one thing, that the capital sigma stands for the sum of, and this is the sum, it's minus the sum of this. Now, remember the distributive principle. If you have, let's say that you have A plus B goes to the products C plus D. So these are the reactants and these are the products. When I say it's products minus reactants, it would be C plus D, that's the sum of the products, minus the sum of the reactants, A plus B. But instead of having these parentheses, just remember it's products minus reactants. The distributive principle says we can remove these parentheses, so it's C plus D products minus A minus B. That negative sign distributes. Okay, so let's go about working this. I'm going to put it in words first before I plug the numbers in. So in this case, the delta H 0 for this reaction is equal to the products. It's going to be the delta H 0 of formation of CaOH2 plus 2 times, so the lowercase n represents the stoichiometric coefficients, the number of moles. Oh, there's just one here. So plus the delta H, it's products, delta H 0 of formation of C2H2 minus reactants, minus the delta H 0 of formation of CaC2 and minus 2 times the delta H, 0 of formation of water. Now again, why is it products minus reactants? Why do I subtract the second one? It's because it's minus the sum of these, and that negative sign is distributive. Okay, so let's plug in what we're given in this case. So this is the relationship that I'm going to use. This is Hess's law as it's applied to this thermochemical equation. Okay. Well, in this case, I know the delta H of the reaction. The delta H of this reaction is negative 127.2 kilojoules. Everything's in kilojoules, so I won't write the units as we're proceeding. This equals the delta H of formation of calcium hydroxide, which is negative 986.2, plus the delta H of formation of C2H2 is positive, so plus 226.7. So these are products. Now, even with the products, if this was already negative, keep it as negative. These are products minus reactants. So minus the delta H of formation of CaC2. And that's what we're looking for. We're trying to determine the delta H of formation of CaC2. This is our unknown. Delta H, 0 of formation of CaC2. And then minus 2 times the delta H of formation of water. The delta H of formation of water is negative 285.8. Okay. So you have one equation with one unknown. Rearrange the equation, solve for the delta H, 0 of formation of CaC2, and that calculates out to be negative 60.5 kilojoules. And so the correct answer is that that's the delta H, the choice C, the delta H of formation is negative 60.5 kilojoules. Okay, now we go to question number 11. This is another application of Hess's law. Hess's law says if a reaction occurs in several steps, the delta H is the same as if it occurred in only one step. So in order to do this problem, number 11, notice that we have what I like to call a target equation. This is what we're aiming at. I would like to know this is the target equation. I would like to know what is the delta H for this target equation. Whereas up here, these are our given equations. These are the given equations. Let me just number this, number 1, number 2, number 3. And the goal is you want to manipulate these equations so that when you add them together, you get the target equation. And here's how you do it. Focus on the target equation. In the target equation, I need 1 mole of C2H4 on the reactant side. In the given equations, the only place I see C2H4 is equation 2. And there is 1 mole, and it's on the reactant side. So I'm going to rewrite equation 2. And since there's 1 mole on the reactant side, I'm going to write it exactly as it's written. C2H4 plus 3O2 reacts to form 2CO2 plus 2H2O. And the delta H is negative 1,411. Okay? So I'll keep the delta H over here to the side. So that's 1 mole C2H4. Next, in the target equation, I need 1 mole of H2 gas on the reactant side. The only place I see H2 gas is equation 3. But there's a problem. I have 2 moles of H2 gas, and I need 1 mole of H2 gas. So I'm going to take equation 3 and divide everything by 2, including the delta H. So I'm going to take equation 3, divide everything by 2. And that's going to give me H2 gas plus O2, and it'd be plus 1/2 O2. I have to multiply each coefficient by 1/2, forms H2O. So divide everything through by 2. Well, I have to divide this by 2 also, so the delta H is negative 572 divided by 2. So that's the hydrogen. Then, in my target equation, I need 1 mole of C2H6 on the product side. Now, in the given equations, the only place that I see C2H6 is equation 1, but I have 2 moles on the reactant side. I need 1 mole on the product side. So I'm going to rewrite equation 1. I'm going to flip the equation and divide through by 2. When I flip the equation and divide by 2, instead of having 4 CO2s, I will have 2 CO2 plus 3 H2O reacts to form C2H6 plus 7 halves O2. I'm dividing everything through by 2, 7 halves O2. Now when I flip the equation, that changes the sign. It's no longer negative 3,120. Okay. So it will be positive 3,120 divided by 2. So when I flip the equation, I change the sign, and when I divide through by 2, I had to divide this by 2. Okay, now when we add these reactions together, do we get the target? Now don't do this in your head. Go ahead and write it out. You can't go wrong. And here's what I do. Everything on the reactant side stays on the reactant side. Everything on the product side stays on the product side. And as you add these together, if something is on both the reactant and product side, for example, here's water on both reactant and product side, then you can cancel them. And I like to underline each value as I come to it. So I have C2H4. So I'm going to have 1 C2H4. It reacts with, well, next I see oxygen on the reactant side. Here I have 3 moles of oxygen, and here I have 1/2 mole of oxygen. So on the reactant side, I have 3½ moles of oxygen. Well, over here on the product side, I had 7/2 moles of oxygen. 7½ is 3½ moles. This is 7/2. This is 7/2. They cancel out. The oxygen cancels out. Next, I have 1 mole of H2 gas on the reactant side. There's no H2 gas anywhere else, so I put plus H2. Okay, so that's the H2. Next, I have 2 moles of carbon dioxide on the reactant side, but that cancels the 2 moles of carbon dioxide on the product side. I have 3 moles of water on the reactant side. That cancels 1 plus 2 is 3 moles of water on the product side, so the water cancels out. Notice that everything on the reactant side is underlined. So we go to the product side, and that leaves the only thing I haven't underlined is C2H6. And so this is my target equation. The reason you do this is to make sure that when you add these equations together, you get your target equation, and I do. So what is the delta H for this reaction? The delta H for this reaction is negative 1,411 minus 572 divided by 2 plus 3,120 divided by 2. And when we do that, we will get negative 137 kilojoules. And so the correct answer is choice B. Okay, number 12 is our last question in this problem set. Number 12 says if you have 2 grams of calcium oxide, so I'm going to put underneath this, I'm going to write 2 grams. We have 2 grams of calcium oxide, is added to 49 grams of water, the temperature of the water increases to 32.3 degrees C. Assuming the heat of the solution is 4.18 joules per gram per degree C, calculate the delta H in kilojoules per mole of calcium oxide for this reaction. Calculate the delta H in kilojoules per mole of CaO. So what is the delta H for this reaction using this temperature? Okay, well, in order to work this problem, I'm going to need a lot more space, so I'm going to take a separate sheet of paper so you can see step by step what's going on in this reaction. So I'm going to, just as in the previous calorimetry problem, I'm going to list the bullet points of what I'm trying to do in this particular problem. Okay, the first thing that I want you to do is I want you to at least think what is the first law expressed in words? The first law of thermodynamics in words. Now, when I say that, the first law of thermodynamics says that energy is conserved. You can't create or destroy energy. Well, how would I apply that to this reaction? Well, I would say the heat lost by blank, always identify what's losing heat and what's gaining heat. The heat lost by blank must equal the heat gained by blank. Must equal the heat gained by blank. So as I look at this, what's gaining heat and what's losing heat? Well, and even before I do this, let's look at this. When you add 2 grams of calcium oxide to water at 25 degrees C, look at the final temperature. The temperature goes from 25 degrees C, let's say 25.0 degrees C. This really needs another significant figure, 25.0 degrees C, to 32 degrees C, 32.3. It's getting hotter. If it's getting hotter, is it endothermic? Is the reaction itself endothermic or exothermic? If it's getting hotter, is the reaction endothermic or exothermic? Well, the reaction is giving off heat. The reaction is exothermic. Therefore, it's exothermic. And what do you know about the delta H of exothermic reactions? I would recommend you do this before you start the problem. If it's exothermic, then the delta H of the reaction is a negative value. And so before doing anything else, you can rule out choice A, which is endothermic, and choice E. It's got to be a negative quantity. This is an exothermic reaction. Okay, so that's what we begin with. This is exothermic. So what's losing heat and what's gaining heat? Well, the reaction is losing heat. The reaction, calcium oxide reacting with water, this is what loses heat. The heat lost by the reaction must equal the heat gained by what? What's gaining heat? The solution. This is, whenever you mix these together, you get a solution. The solution is gaining heat. So now you don't have to write this down, but you've got to mentally think it. Now write this down using our symbols. What is the symbol for heat? It's Q. So I would write Q of the reaction equals Q of the solution. Now that's almost correct, but it's not quite correct. If the reaction is losing heat, that's negative. If the solution is gaining heat, that's positive. So I need a negative sign. I can put the negative sign on either side. I think I'll put a negative over here. Okay. You can put it on either side. It doesn't matter. So my bullet point that I'm going to list over here as we work this problem is to say, why the negative sign? So here, why the negative sign? There's a negative sign because the reaction is losing heat. Q of the reaction is negative. The solution's gaining heat, which is positive. So a negative times a positive makes this whole number negative. Next, in a previous problem, we did MCAT. But the third point I want to make here is I want to say this is an important statement. We cannot determine the Q of the reaction using MCAT. But we can determine Q of the solution using MCAT. But we can determine the Q of the solution using MCAT. Now here's what I mean. Now this is the important point. This is the key point. This is a hard problem if you don't make sense of this. And that is the Q of the solution is equal to the mass of the solution times the specific heat of the solution times the delta T of the solution. I can calculate how much heat the solution changes. Okay, so let's do that calculation. Q of the solution is equal to the mass of the solution. Now, as you look at this the problem, the mass of the solution is the mass of the calcium oxide plus the mass of the water. 2 plus 49 is equal to 51 grams. So it's the total mass of the solution. What is the specific heat of the solution? Well, we're told, assuming that the specific heat of the solution is 4.18 joules per gram per degree C. This should have the word specific heat. Assuming that the specific heat of the solution is 4.18 joules per gram per degree C. Okay. What's delta T of the solution? Well, remember, delta T is always T final minus T initial. What's the final temperature? It's 32.3. What is the initial temperature? 25.0. Now, whenever we do this, what we're going to end up with in this particular case is, for this value, this would be 7.3 degrees C. And so when we multiply this through, we will get the Q of the solution. We'll get the Q of the solution. Okay. And the Q of the solution calculates out to be 1,556 joules. Okay. But remember, we calculated Q of the solution. The solution gained heat. That's what we measured. And therefore, we know the Q of the reaction. So, therefore, the Q of the reaction is equal to negative 1,556 joules. Okay. The solution is gaining heat. Where did that heat come from? It came from the reaction. The heat lost by the reaction must equal the heat gained by the solution. The solution is gaining heat. We calculate the heat of the solution using MCAT, and the reaction, therefore, is losing that much heat. Okay? Now, the next thing that you have to notice, remember this is asking, calculate the delta H for this reaction, the delta H0, and the delta H is always the coefficients represent the number of moles. The delta H for this reaction is for 1 mole of calcium oxide. Did we react 1 mole of calcium oxide? No, we reacted 2 grams. We reacted less than 1 mole. So the next bullet point that I would make here. So point number 4, and this is also an important point. I'm going to highlight this. And that is that the delta H0 for the reaction is for 1 mole. This is what we're looking for. This is for 1 mole of calcium oxide. Now, do we have 1 mole? No, we had 2 grams. And so the number of moles of calcium oxide that we had in this problem is equal to 2 grams of calcium oxide times 1 mole of calcium oxide per, from the periodic table, 56.08 grams of calcium oxide. Okay, so this is the molar mass. And so, therefore, the number of moles of calcium oxide is equal to 0.03566 moles of calcium oxide. So, look at this. We calculated how much heat the reaction released, but the reaction didn't have 1 mole. It had 0.03566 moles. And so, to answer this question, the delta H for this reaction is going to be is equal to the Q of the reaction divided by the number of moles of calcium oxide. So the delta H of this reaction calculates out to be negative 1,556 joules, so we get that from this step up here, divided by the number of moles of calcium oxide, 0.03566 moles of calcium oxide. That calculates out to be negative 43,600 joules per mole of calcium oxide, or the delta H of the reaction is equal to negative 43.6 kilojoules per mole of calcium oxide. And that means that the answer to this question ends up being choice B. So the answer to this question ends up being choice B.